Hey everyone, Akil from Oxford Academy here. Today we will be talking about the integral, the second fundamental tenet of calculus. It is taught in many Calculus 1 classes in college. So, what we're going to start off with is the conceptual definition of an integral. Right here, this is sort of the mathematical limit definition of an integral. As you can see, it is unbelievably complicated. You see we have a limit, then we have a sum, and then we have like f of x of I, and then we have like b minus a over n, but we're summing to infinity. So it appears to be like L'Hopital's rule, but it's not L'Hopital's rule because there's a sum. As you can see, it gets extremely convoluted. But this right here, this crowbar from a to b of f of x dx, this right here is the notation for the integral. So let's actually try to get a conceptual understanding of what the heck this definition means. So let's go ahead and take a look at this graph f of x here. So as you can see, we have the graph y is equal to f of x. This is just a continuous function from from 0 to infinity. And we have bounded values of a and b for x, all right? So what we can do is we can say that the integral represents the area under the curve. Now, what do we mean by that? Well, we can actually go ahead and find the area that's bounded between this curve right here, a and b, and the x-axis. This right here, this area is the integral from a to b of f of x dx. That's what the word definition of an integral is. But we want to prove why that's the case. So what we can do is let's not try to find the exact area of the integral or the area under the curve straight away because it looks pretty much impossible. Let's try to approximate this area first. So what I'm going to do is I'm going to draw two relatively large rectangles. So we're going to have something like this for our approximation of the area. So I just chose 3 rectangles, and as you can see, it looks pretty inaccurate. Now, why does it look inaccurate? Well, you see, we have this area unaccounted for, and we have an excess of this area and this area right here. So this is actually an overestimate of the actual area under the curve. But what if we crammed more rectangles into the space of A and B? What if we crammed more rectangles? Maybe we might get a more accurate estimate. So let's check it out. So I'm just going to go ahead and add in 6 rectangles now. So if we go ahead and draw in these new rectangles, it's still not going to be completely accurate, but you can actually see that it does look a little bit better, doesn't it? This is actually a little bit confusing of a drawing, but I'll go ahead and get rid of some of the excess red stuff. But as you can see, if we go ahead and try to mark in the excess and unaccounted for areas, you can see that it's actually a lot less than what it was before. And so therefore this gives us the idea, what if we crammed in an infinite amount of rectangles between A and B? You can see that the margin of error here that's represented by this excess area, that's going to get so infinitesimally small, you can consider it to be 0. So therefore, if we had just an infinite number of rectangles, which I'll go ahead and represent as lines, we just had an infinite number of these, and obviously these aren't going to be perfect lines, but as you can see, we can pretty much get the exact area under this curve just from an infinite amount of rectangles. Now, what does that mean? What are the areas of these actual rectangles? So, to actually check out what the areas are, let's go back to our more crude example where we had less rectangles and there was more error. as you can see, this maps to a value of f of x, and we know it's going to be f of b, but we don't really care about that. This is also an f of x. This is an f of x, and so on and so forth. But what is this with under here? Let's call this with delta x. And what delta x actually is just b minus a divided into n rectangles. Now, why is that? Well, you can think about it geometrically. If we have this distance b minus a, and then you divvy it up among a finite amount of rectangles, then you would just have delta x as one of the 6 divvied up areas, or 1/6 of b minus a. So we can say that delta x is b minus a over n. And if we go ahead and take a look at this area, the area is just going to be f of x of some index I, for example, times delta x. If you wanted to sum up all the areas of the rectangles, we can actually call this area I. So we can say area is equal to the sum of each area. And we know that this is going to be equal to the sum from 1 to n of f of xi delta x. Now, remember what we said earlier. We said that we were going to cram an infinite amount of rectangles into this. This n right here, this n represents the number of rectangles because we're adding up that number of areas. So, the actual area under this curve is going to be the limit as n goes to infinity of I equals 1 to n of f of x initial, or f of xi, times delta x, and we already said that delta x is b minus a over n. As you can see, we've pretty much just derived this definition of an integral here. So yeah, in conclusion, the definite integral, or the area under a finite curve, or should I say an area under a curve in a finite range, a finite bounded range, this is equal to the sum of a bunch of infinitesimally small areas with little to none margin of errors. And as a result, you will get the exact area under the curve. So that concludes this video on the definition of the integral. Thank you for watching, and I hope to see you in future videos.